Black holes are among the most mysterious objects in the cosmos, extensively studied yet not entirely understood. Contrary to their name, black holes are not holes but massive concentrations of matter squeezed into tiny spaces. Get close enough to a black hole and you'll find the event horizon, a boundary beyond which nothing, not even light, can escape due to strong gravity. It marks the outer edge of the black hole, where the escape velocity equals the speed of light. Inside the event horizon is the singularity, a point of infinite density where the laws of physics break down. The event horizon acts as a barrier that prevents observing what happens beyond it, shielding us from the extreme physics near the singularity.
The message of this lecture is that black holes ain't as black as they are painted. They are not the eternal prisons they were once thought. Things can get out of a black hole, both to the outside and possibly to another universe.
We've all heard the scary stories of a black hole swallowing the sun. Luckily, that's highly unlikely. But what if, in a crazy turn of events, there already is a black hole inside our sun, slowly consuming it from within? Stephen Hawking proposed this remarkable idea in 1971. He suggested that our sun could harbor a black hole, not the giant ones we usually think of, but a smaller type called a primordial black hole, theorized to have formed in the early universe. Today, let's explore this cosmic mystery and consider what it could mean for our sun, or any star for that matter, to contain a primordial black hole. How could we detect its presence, and how could uncovering this mystery illuminate our understanding of dark matter? The universe might teem with small black holes, some as tiny as an atom, yet weighing as much as a skyscraper. These primordial black holes, born in the cosmic aftermath of the Big Bang, could be drifting through the cosmos, largely unnoticed until now. For decades, astronomers pondered the possibility of stars harboring black holes at their cores. Back in the 1970s, when researchers realized that the sun wasn't emitting enough neutrinos compared to the energy it was producing through fusion reactions, they proposed intriguing theories. Neutrinos, often dubbed the ghost particles of the cosmos due to their elusive nature, possess fascinating characteristics. Neutrinos, electrically neutral and highly light particles, interact weakly with matter and are produced when atomic nuclei come together, such as in the nuclear fusion reactions in the sun's core or in particle accelerators. They're also produced when cosmic rays interact with atmospheric molecules like nitrogen and when nuclei break apart in a nuclear reactor. The sun produces neutrinos that carry away around 2% of its total energy output. Supernovas are also a significant source of neutrinos, as they are the only particles that penetrate the dense material produced in a collapsing star. One such theory, put forth by Stephen Hawking, suggested that the sun might contain a hidden black hole at its center. According to this idea, the energy shortfall could be compensated by matter falling into the black hole, generating the needed energy without producing detectable neutrinos. However, the mystery was eventually resolved with the discovery of neutrino oscillations. Neutrinos come in three flavors: electron, muon, and tau neutrinos, associated with charged leptons. Produced in various processes like nuclear reactions in the sun, neutrinos undergo oscillations as they travel through space, changing from one flavor to another. These oscillations, where neutrinos change properties as they travel, clarified the discrepancy in neutrino detection. It explained the deficit in solar neutrino flux, resolved by experimental observations indicating neutrinos have mass and their flavors mix quantum mechanically. Despite resolving the solar neutrino problem by detecting neutrino oscillations, the theoretical scenario of stars capturing small primordial black holes remains. So what are these stars, most commonly known as Hawking stars? Named after Stephen Hawking, who proposed the existence of such black holes, Hawking stars are theoretical stars with a small primordial black hole in their core. Theoretically, primordial black holes come in various sizes, from as light as asteroids to as massive as stars, and should be abundant in our universe. Despite their potential existence, these miniature black holes have eluded discovery, as they can only be detected when they interact with surrounding matter, such as when matter spirals towards them and emits light energy. However, the matter must be close to the black hole for this interaction. One intriguing possibility is that black holes play a role in seeding the formation of stars or are present during the star formation process. In January 2022, NASA's Hubble Space Telescope captured evidence of a smaller black hole in the dwarf galaxy Henais 210 creating stars. Matter falling into the black hole was redirected by magnetic fields into outflowing jet streams, and that compressed outflow slammed into a dense cocoon of nearby gas, thereby creating new stars. Ultimately, the evolution is highly sensitive to the accretion physics, researchers note. Accretion physics focuses on how gas or matter accumulates onto compact objects like black holes, neutron stars, and white dwarfs. This process fuels the universe's most influential events, from distant quasars to tidal disruption events in our galaxy. Accretion disks, formed as material falls onto these objects, play a key role in various astrophysical phenomena, including the formation and evolution of planets outside our solar system. In a Hawking star, the black hole at its center grows slowly because the outward-directed luminosity hinders gas inflow to nourish the black hole. Recently, an international team of scientists simulated the evolution of such stars, considering various initial masses for the black hole and different accretion models for the stellar core. Their surprising finding: when the black hole's mass is small, they discovered that these stars can endure for extended periods, and the star appears virtually identical to a regular star. Our Sun could even host a black hole as massive as the planet Mercury at its core without us noticing, explains Earl Bellinger, a researcher at the Max Planck Institute for Astrophysics and now assistant professor at Yale University. They also go on to mention stars hosting very low-mass primordial black holes could have exceptionally long lifespans. Astronomers now consider that primordial black holes could contribute significantly to the universe's missing mass, known as dark matter. Although invisible, this mass influences visible matter gravitationally, enabling astronomers to detect its presence indirectly. Astronomers might also detect these stars using asteroseismology, which we will discuss later. This would offer a way to explore the presence of primordial black holes and their role in dark matter. Black holes are often thought to drain energy from a star, but in reality, they serve as the nuclei of the most efficient engines in the universe. As matter nears a black hole, it accelerates to near-light speeds, generating extreme friction and correspondingly high temperatures. This results in brilliant radiation, such as the radiation emitted by quasars, fueled by colossal black holes in a feeding frenzy. These black holes are the most powerful engines in the universe, capable of driving the most energetic processes, like relativistic jets. The energy yield of a black hole is immense, with the most efficient nuclear fusion only exploiting 0.7% of the available energy. In comparison, black holes can reach up to 50% efficiencies, billions of times more efficient than petrol burning. This high efficiency is due to converting gravitational potential energy into radiation as matter falls towards the black hole. In the years following Hawking's initial proposal, the idea of primordial black holes has gained significant traction. One compelling reason is the enduring mystery of dark matter, a substantial yet unseen component of the universe's mass. While the prevailing theory suggests that dark matter consists of undiscovered particles, the possibility that it consists of numerous primordial black holes cannot be ignored. Primordial black holes could hold the key to dark matter mysteries by M. Mitchell Waldrop, published in the Proceedings of the National Academy of Sciences, PNAS. Despite decades of research, the nature of dark matter remains elusive, with theories ranging from weakly interacting massive particles or WIMPs to hypothetical particles like axions. Initially, the concept of primordial black holes was met with skepticism, but recent developments have shifted the perspective. Gravitational wave experiments conducted by the Laser Interferometer Gravitational Wave Observatory, LIGO, have provided intriguing clues consistent with the existence of primordial black holes. These experiments detected black hole mergers with masses aligning closely with predictions. However, ongoing research explores observational constraints on the abundance and sizes of primordial black holes in today's universe. While they offer a compelling solution to the dark matter puzzle, their formation presents a significant challenge. The equations governing their formation are finely balanced, requiring precise conditions in the early universe. Despite these challenges, upcoming experiments such as the Laser Interferometer Space Antenna, LISA, hold promise for shedding further light on the primordial black hole dark matter hypothesis. With continued advancements in technology and observational techniques, astronomers remain hopeful that the mysteries surrounding dark matter and primordial black holes will be resolved in the coming decades. Earl Bellinger from Yale and the Max Planck Institute and Matt Kaplan at Illinois State have authored research papers exploring the intriguing interplay between primordial black holes and evolving stars. Both studies conducted thorough simulations to observe the fate of Sun-like stars, both with and without primordial black holes, tracking their evolution. Let's start by examining how their model portrays the evolution of a typical sun. We can visualize this evolution on the Hertzsprung-Russell diagram, which charts luminosity against surface temperature. The diagonal dashed lines represent the sun's radius. The point labeled ZAMS denotes where the sun began 4.6 billion years ago. Over time, the sun has gradually become brighter and hotter, shifting to its current position. However, its core will deplete its hydrogen fuel in a few billion years. This will cause the outer layers to expand and cool, transforming the sun into a red giant. Eventually, it will expand to hundreds of solar radii, potentially engulfing Mercury, Venus, and Earth. Finally, the sun will shed its outer layers, leaving behind an ultra-dense white dwarf roughly the size of Earth. This progression seems straightforward, but what changes when introducing a black hole? Earl Bellinger has proposed scenarios if a primordial black hole is in the sun. Exploring Bellinger's research team's model, which predicts the sun's behavior and evolution based on our current understanding, and then observing the scenario when a primordial black hole is introduced, things proceed much like they would without a black hole for the first few billion years. However, the small black hole gradually begins to accrete matter in this case. Anything within a certain distance of the black hole gets drawn towards it, forming what's known as the Bondi sphere. Matter doesn't undergo fusion within this sphere, but generates energy through friction as it collides around the black hole. This disrupts the core's center, causing the surrounding material to churn like a bubbling cauldron. Consequently, the inner core becomes convective. This convection becomes significant later on because although the core is hot enough to fuse hydrogen into helium, it's not hot enough to fuse helium into heavier elements. This allows the rest of the core to continue fusion uninterrupted. However, with convection, helium nuclei are mixed back into the surrounding plasma. While this doesn't halt fusion completely, it decreases the fusion rate slightly. Throughout most of the Sun's lifespan, convection remains confined to the very center of the core, causing no significant slowdown in its energy output. By the time the Sun reaches its current age, the black hole has grown to the mass of Mercury. Although enlarged, it remains tiny, with a radius less than 1/10 of a millimeter or about 0.039 inches. The Bondi sphere has expanded, but is still only a few centimeters across. While the convective region extends further into the core, it's still no more larger than Earth. From the Sun's perspective, everything appears normal. However, it's intriguing to consider that at this moment, the Sun could harbor a black hole as massive as Mercury, yet we would have no way of detecting its presence. As the black hole grows, its gravitational pull on its surroundings strengthens. Additionally, its size increases, drawing more matter into its widening grasp. The radiation emitted from the accretion process also intensifies, causing the convective bubble to expand further into the fusing core. Usually, the core would contract as helium accumulates at its center. However, the convection caused by the black hole has the opposite effect, expanding the core and pushing the fusion zone away from the center. After 5.5 billion years, the black hole has grown to a few hundred thousandths of the Sun's mass and contributes about 20% of the Sun's luminosity. The convection zone has expanded so much that fusion in the core starts to decline rapidly. The Sun's evolution reverses on the diagram, growing fainter and cooler. Its end draws near. The black hole soon reaches a mass 1/10,000th that of the Sun. This is akin to compressing the planet Uranus into a 10-centimeter ball. Although the black hole is no larger than a grapefruit, its convective bubble expands to engulf the entire star. The core disappears, pushed outward into the upper layers, where fusion ceases. The Sun now relies entirely on black hole power. As the black hole grows, the increasing radiation inflates the outer layers, causing the Sun to prematurely expand into a red giant billions of years ahead of schedule. However, this expansion is short-lived. With less material in the interior, the black hole's growth and radiation output stabilizes. The Sun's expansion halts approximately 4 to 5 times its current radius. Instead of engulfing Mercury, Venus, and Earth, the Hawking Sun can't even reach Mercury's orbit. However, it still shines about 10 times brighter than today, enough to vaporize the oceans and turn Earth into a charred husk much sooner than anticipated. The not-so-giant Sun spends the next several billion years as a sub-subgiant. Perhaps later, it evolves into a red straggler. The precise outcome hinges on how the black hole continues to accrete and whether photons can escape the accretion or become trapped in orbit around the black hole. However, the outcome remains unchanged. The black hole gradually devours the Sun from the inside out. This isn't surprising. It's a growing black hole. What is surprising is the longevity of the Hawking Sun, even with various initial black hole masses. So far, we've examined a black hole starting with a mass 100 millionth that of the Sun's and observed its growth from there. However, if the Sun began with a black hole only 1 trillionth of the mass of the Sun, Its presence wouldn't be noticeable until after the Sun had exited the main sequence. It's only when modeling black holes, starting with masses comparable to those of dwarf planets, that the Sun's evolution could occur earlier than its current age. Nevertheless, nobody, not even the authors, believes the Sun harbors a black hole. Yet, if evolved Hawking stars exist, there may be a chance of discovering them.
Stars are made out of gas, and so my goal in astroseismology is to measure the sound speed throughout the entire interior of a star and use that to see inside the star.
Sound speed, or waves, travel through a star's interior due to temperature changes originating in the convection zone near the star's surface. This process is akin to bubbles in boiling water or a drum. These waves cause the entire star to expand and contract, essentially ringing like a bell. Unlike seismic waves on Earth or quakes on the Moon and Mars, stellar sound waves are continuously generated by turbulence near the star's surface. These vibrations result in slight flickering in a consistent pattern or are observable as localized brightening and dimming. We can analyze this flickering using astroseismology to gain insights into the star's interior. While astroseismology cannot penetrate the core, it can delineate the boundary between the convective upper layer and the interior radiative layer. By studying these waves in stars of various sizes and ages, scientists gain insights into stellar properties and evolution, including predictions of our Sun. An evolving Hawking star would be entirely convective, leading to a much simpler oscillation mode detectable by asteroseismology. ESA's Gaia satellite has identified approximately 500 red stragglers. Once its asteroseismology data is available, the team will scrutinize them to determine if they might contain indications of potential Hawking stars. Although now retired, NASA's Kepler Space Telescope played a crucial role in this revolution by providing observations of waves in tens of thousands of stars following its launch in 2009. NASA's Transiting Exoplanet Survey satellite, TESS, launched in April 2018, is expected to observe sound waves in up to 1 million red giants, the massive evolved stars that will represent our Sun's future appearance in about 5 billion years. While both Kepler and TESS are renowned for their exoplanet hunting capabilities, they also serve as powerful tools for detecting stellar vibrations. Moreover, the more we learn about stars, the better we understand the planets that orbit them. We are using seismology to provide an exquisite characterization of the host stars, and hence the planets we've discovered, explained William Chaplin, a professor of astrophysics at the University of Birmingham, United Kingdom, who leads Kepler's astroseismology effort for sun-like stars. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. Thank you for listening. As we conclude our exploration of hidden black holes and the mysterious lives of stars, remember that our universe is entirely of remarkable wonders, sometimes hidden right before our eyes. While the idea of our Sun containing a secret black hole might seem distant, it's an intriguing possibility worth exploring through astronomy and science. If you liked learning about space, please subscribe and hit the notification button for more cool stuff about science and space. Stay tuned for more amazing adventures in space. Thanks for joining us, and see you on the next journey.